Hi viewers, welcome to my class on thermal stresses. So in this class, I'll explain how thermal stresses are induced in materials, and later we will work out a numerical example to calculate the thermal stresses induced in a bar. When a material is subjected to temperature change, the material either expands or contracts. If this expansion or contraction is prevented, thermal stresses will be induced in the material. Most of the engineering materials undergo an expansion when they are heated. Now, if this expansion is completely constrained, as shown in this figure, by supports, and this bar is heated, the tendency of the bar is to increase its length. So it is trying to expand, and the supports are not allowing this expansion, and the support has to, in that case, exert a compressive force to retain its length. So it is trying to expand, supports are not allowing this expansion, so to prevent that expansion, supports has to exert a compressive force. So this is when the bar is heated. Bar is heated, it's trying to expand. This expansion is prevented by the constraint, and it exerts a compressive force on the bar to retain its length to L. Now suppose a material is cooled, it tries to contract. So contraction means length is trying to reduce. So it will exert forces on the walls to contract. So in turn, to keep the length to this length L, the supports has to exert a pull. Okay, it's trying to contract. This rigid support has to exert a pull on the bar to retain its length L. So when it is trying to contract, support will exert a pull, or tensile stress will be induced in the material. And if it's trying to expand, support has to exert a compressive force on the bar to retain its length. So if expansion or contraction is prevented, thermal stresses will be induced, and if the expansion is prevented, the thermal stress induced is compressive, and if the contraction is prevented, thermal stress induced will be tensile in nature. So if a bar is freely expanded, freely allowed to expand, okay, then no thermal stress will be induced. It will expand by an amount alpha L delta T, where alpha is the coefficient of linear expansion, and L is the length, and delta T is the temperature change. So no thermal stresses will be induced in the material when it is free to expand. Only when it is constrained, the stresses will be induced. So if it is freely permitted to expand or contract, no stresses will be induced in the material. Now let us consider a bar which is fully constrained, that is, it is rigidly supported at the ends, and it is heated. So when it is heated, the tendency of the bar is to elongate. Assume that this constraint is not existing, then the bar would have elongated by alpha L delta T. So this is the expansion, free thermal expansion in the absence of support. Now what is the function of the support? When support is existing, support is exerting a force to prevent this expansion and to retain the length L. So support is exerting a compressive force to prevent this expansion and keep the length to L. So we can consider this as the initial state. Now we can consider like this: you are allowing the bar to expand, and then later on a force is applied to bring back its length to final length L. So this can be considered as initial state, which is a natural state after heating, and this is the final state. Now you can find out the temperature strain like this. So this is taken as initial state, So length is L plus alpha L delta T, and final length is L. So due to this compressive force applied, final length is reduced to L. So LF minus Li by Li will give the thermal strain, or any strain for that matter. Final length minus initial length divided by initial length will give the strain. In this case it is thermal strain. Now Li is L plus alpha L delta T, and final length is L. So L minus L plus alpha L delta T divided by initial length is L plus alpha L delta T. So L minus L, that cancels, minus alpha L delta T divided by L plus alpha L delta T. Now you can neglect alpha L delta T in the denominator, which is very small compared to the length of the bar, because alpha is very small, and for a given temperature change alpha L delta T will be small. So you get minus alpha L delta T divided by L, and L cancelled. In that case you will get the temperature strain is minus alpha delta T. Now once the strain is known from the Hooke's law, you can write the temperature stress sigma T as strain multiplied by Young's modulus, or you get the temperature stress as minus alpha delta T E. So alpha is a coefficient of linear expansion, delta T is the temperature change, and E is the Young's modulus of the material. So this expression will give the sign convention for the stress also. If you are taking this expression for calculating the stress, it will give the nature of stress also. So delta T, when it is increase in temperature, delta T will be positive. Final temperature minus initial temperature, that is delta T. So if it's an increase in temperature, delta T is positive, and in that case you will get a negative value. And if it's a decrease in temperature, delta T will be negative. So in that case minus of minus will make it plus. You will get a positive stress, that means tensile stress. So if expansion is prevented, then you get a negative stress or compressive stress, and if contraction prevented, you will get a positive stress. This formula is for complete prevention of expansion or contraction. So if expansion is prevented, you will get delta T positive, and the stress will be negative. If it's a contraction, delta T will be negative, you will get a positive value, and if a contraction is prevented, the formula will give a positive value of stress, that means tensile stress. So this is a expression for the complete prevention of expansion or contraction. No amount of expansion or contraction is permitted in the bar. Now let us consider a case where you are permitting partial expansion or contraction. When it's heated, the natural state is to expand and maintain a length L plus alpha L delta T. Now the supports are not completely rigid. It permits some amount of expansion delta A. So it is permitted some amount of expansion. So delta A is the permitted expansion. So supports, when it is heated, so the supports are yielding. So supports are going backward and by an amount del A. So assume this is a rigid support, and this is while heating, when it tries to expand, the support is moving by a small amount del A. So much expansion is permitted, but the bar is trying to expand by alpha L delta T. So much is not permitted, it permits only del A. So this is a natural state, or you can consider this as an initial state, and again compressive stress is induced because it is not allowed to expand freely. Some amount of constraint is there, so the constraint is exerting a compressive force to reduce the length from the natural state. So compressive force is acting on it, but the amount of compressive force will be less because some amount of expansion is permitted in this. So here now let us take the this as the initial state and this as a final state. Let us take like this. It is heated and it is expanded freely. Now the compressive force exerted by the support is bringing back its length to L plus del A. So that is the final state. So initially you are permitting expansion and then compressive force is slowly bringing back its to final length L plus del A. So LF is L plus del A minus initial length is L plus alpha L delta T divided by L plus alpha delta T, that will give the temperature strain. Now L plus del A minus L plus alpha L delta T, L cancels, you get del A minus alpha L delta T divided by L plus alpha L delta T. So again in the denominator you may neglect this alpha L delta T and you will get del A minus alpha L delta T divided by L as the temperature strain. And you can find out the temperature stress by multiplying this with the Young's modulus of elasticity. So this is a thermal strain, and multiplying this with the Young's modulus you will get the thermal stress induced. So stress induced is that del A minus alpha L delta T divided by L into E. So this formula can be used to find out the thermal stress, and you will also get the sign convention for thermal stress when delta T sign is considered. But you cannot blindly use this formula, since del A cannot be greater than alpha L delta T. Expansion permitted cannot be greater than alpha L delta T, because alpha L delta T is the maximum free thermal expansion. Now permitted expansion cannot be greater than alpha L delta T. So in all the cases you should check that alpha L delta T value and compare it with the del A, and if alpha L delta T is greater than del A only, you should apply this formula. So if delta T is positive, and this term has to be always greater than del A, when delta T is positive you will get a negative sign for this, and delta T is negative you will get plus, and del A is also going to be negative in that case, negative. If it's contraction then you should take it as negative, permitted contraction you should take it as negative. So this is minus and del T is minus, you will get plus, and you will get a positive stress in that case. So instead of using this formula based on sign convention, you can take it as alpha L delta T minus del A divided by L into E as the stress induced. And also remember that alpha L delta T is always greater than del A. It should be always greater than del A, then only you should apply the formula. So this is without sign convention. You need not take the sign convention for delta T. So the magnitude only, let us work. So the magnitude of this del T, only temperature change you substitute. Don't take it as a final minus initial. So substitute the temperature change and substitute the magnitude of the permitted expansion, whether it's contraction or expansion permitted, you take it as positive. And del T also, only temperature change, just substitute the magnitude, that will give the thermal stress induced. And you know, heating, if at all stress is induced, it should be a compressive stress, and cooling, if the stress is induced, it should be a tensile stress. So you will get the magnitude of the thermal stress, and then you can decide whether it's a compressive stress or a tensile stress based on the whether it is heating or cooling. Only thing you have to check that alpha L delta T, this temperature change, okay, alpha L delta T should be greater than del A. Only thing is alpha L delta T should be greater than del A. Now let us work out a numerical example. A copper rod 60 mm diameter and 600 mm long is fixed between two rigid supports. The temperature of the rod is raised by 40 degrees centigrade. Find the stress induced in the rod due to this temperature change. The Young's modulus of copper is 100 gigapascal and the coefficient of thermal expansion is 18 into 10 raised to minus 6 per degree centigrade. Also determine the stress induced in the rod if the support permit the expansion by 0.3 mm. So it's a copper rod 60 mm diameter and 600 mm long, and it is fixed between two rigid supports. You are increasing the temperature by 40 degrees centigrade. So the temperature change is 40 degrees centigrade, raised by 40 degrees centigrade. So delta T is 40 degrees centigrade, length is 600 mm, diameter is 60 mm, and the Young's modulus of copper is 100 gigapascal. E is given, coefficient of thermal expansion alpha value is given. So first case is when it is completely constrained, you need to find out the stress induced, and second part is when permit an expansion, thermal expansion of 0.3 mm, find the stress induced. Now the length of the rod is given, diameter, temperature change, Young's modulus 100 gigapascal per 100 into 10 raised to 3 Newton per mm square, coefficient of thermal expansion alpha 18 into 10 raised to minus 6 per degree centigrade. Now thermal stress when the material is totally constrained, you can find out as alpha delta T. That is first case. When there is a completely constrained from expansion, you can find out the thermal stresses alpha delta T. I not taken the sign convention. I not written as minus alpha delta T. Alpha delta T will give the magnitude, and we know in this case it is an expansion, only compressive stress will be induced. So alpha value is substituted, delta T is 40 and the Young's modulus is 100 into 10 raised to 3, which will give the stress as 72 Newton per mm square, and the stress is compressive since heating only produces compressive stress. So the bar will be subjected to a compressive stress of 72 Newton per mm square as a result of this heating, and the bar is completely constrained. No amount of expansion is permitted. In that case 72 Newton per mm square or 72 megapascal of compressive stress will be induced in the bar. Now let us consider the second case where free expansion is 0.432 mm, alpha L delta T which is 0.432 mm. The permitted expansion is 0.3 mm. So you are allowing an expansion of 0.3 mm. Now a free expansion is more than the permitted expansion. In that case stress will be induced. So in case del A is more than 0.432, no stress will be induced. You are allowing more than the free expansion. In that case no stress will be induced. You cannot blindly use the formula. So only when free thermal expansion is greater than the allowed expansion, you can apply the formula. So here free thermal expansion is more than the permitted expansion, so stress will be induced in the rod. Now the temperature stress you can calculate is del L minus del A into E divided by L. So del L is free expansion 0.432, del A is permitted expansion 0.3, Young's modulus is 100 into 10 raised to 3 divided by length is 600. You will get the value as 22 Newton per mm square or 22 megapascal. So because of this partial expansion, the stress induced in the bar is reduced. So it is only inducing 22 megapascal stress, and you know that it is can induce only compressive stress because your heating can induce only compressive stress. If it is a cooling and if you are constraining, then it will induce a tensile stress. So I did not take the sign convention. I just worked on the magnitude. So I got the stress and I know that it is a compressive stress. So when some amount of expansion is permitted, the stress induced in the bar is reduced. Earlier it was inducing 72 megapascal of stress. Now after permitting some amount of expansion, the stress induced is reduced to 22 megapascal. If it's complete free expansion, no stress will be induced in the material. That's all for today. Thank you for watching.